Hans, are you coming back?
Yes, back in time.
Okay, yes. Hello, good morning. This is the podium from NC State University. Welcome you again to the world largest river and the delta system, the Source to Think online webinar series. Today, we invited Dr. Hansjörg Seybold from Swiss Federal Institute of Technology. I believe is the ETH, is the local, should be say ETH, Zurich. So before I introduce Hans, as usual, we will see the next webinar, the next Wednesday, September 2nd. We will invite Professor Irina Uverin from University of Colorado Boulder. She will talk about the Greenland sediment flux. And that's an amazing study, because before we underestimate how much sediment those white island could transport to the ocean. So please mark your calendar coming back next Wednesday. Okay, Hans, this is a snapshot from his website and his CV. As you can see here, he's a senior research scientist in ETH, Zurich, Department of Environmental Science. He got his master degree from University of Stuttgart in Germany, and then PhD from ETH Zurich in 2009, and then spent 4 years as a postdoc at MIT, United States, and then back to ETH Zurich, and also have some experience visiting professor in Brazil and other places. So Hans, thank you very much. Today, you like to give us talk about the controls of the channel network from the source to the sink. So Hans, now is your turn. Please share your screen.
Okay, let's make it in presentation mode. Can everybody see it? So I would like to thank Paul for organizing this webinar series, and thank him for the opportunity to present here some results of some recent work I've been doing with Walter Berkers here at ETH. And I will present it in a broader context of the question, what controls the geometry and shape of channel networks in general. Before I start with the question on control, I would like to clarify a few terminologies, and also to show how the channel network is important for the whole landscape in all. Paul asked me when I sent him the title why I didn't use the word river networks. So in the following, the word river will be used for the hydrological feature that has the flowing water, which creates, for example, subaqueous bed form, channel bars, or meanders, while I'll use the word stream, valleys, or channels rather loosely interchangeable for the geomorphological feature in the landscape that accumulates the water and usually has the flowing water inside. And this second perspective also shows the importance of the channel network within the landscape itself. And I found two quotations on the web, which the first says, channel incision drives the topographic evolution of mountain ranges, meaning that what happens here at the bottom of the valley actually controls what happens here in the mountains above the clouds in this case. On the other hand, the channel is not at a random place. It is where the topography puts it at the bottom of this valley, and it doesn't run along the ridge lines. And these two different perspectives already show how the channel network and the surrounding topography is coupled with each other and cannot be seen as separate entities. And I once summarized this in a sentence which sounds as follows: that flows shape landscapes and landscapes shape flows, which means the way how water flows. So to describe the controls of how the geometry and topology of stream networks is controlled, I will pick up the title of the webinar series and walk along the channel network from the headwaters at the source, along the main paths of the channels to the outlet at the delta, where I will start with some results we obtained from the Rothman group at MIT on seepage channels. Then I will have the larger controls of the main river networks, and finally show a few slides where John Shaw's group applied the theoretical descriptions we obtained for the headward growth on the distributary channels at the outlet. So closing the theoretical loop from source to sink and back. So let's start with part one. The question how channel networks grow, how they ramify, has been a topic in geomorphology even long before the seminal paper of Montgomery and Dietrich, who asked, where does the channel begin? And getting the flow on the topography and the interaction right is rather a complicated thing, which we still try to understand. And therefore, we will start with a simplified case, which is channels incised by subsurface flow, which means we have a groundwater field that emerges in a spring and then forms a channel. Here, the system of the groundwater flow is more or less linear system of equation. It is less sensitive to the topography, and it reflects the competition of the different channels with respect to groundwater. To show you a few pieces where such type of channels can be seen on the very small scale. Everybody may have seen this at the beach when the tide retracts and the water seeps out of the beach sand. On a larger scale, you can find them on the coast, where the groundwater flowing down from the mountains seeps out and ends into the ocean. And you definitely find this kind of channels in a field site, which we use to compare our theoretical results, which is on the Florida Panhandle, here close to Tallahassee, where this is the Apalachicola River, and here the ravines incised. And from this aerial photo, we can nicely see, because people cut most of the pine trees in between the ravines. And if you walk to the rim of the valley network, you see it goes quite steep down. And this is how the channels look when you are inside such a valley. But more about this later. So the conceptual model, how such channel networks grow, was already proposed 40 years ago by Thomas Dunne, where he hypothesized that if you have a small perturbation on the sidewall of a channel, it leads to a focusing of the flow, and therefore to more flux, which in consequence should also lead then to more erosion in this direction. So a mathematization of this growth hypothesis would be that we have a field, which in this case is the groundwater flow, and we have a rule that the channels grow in the direction of the flux into the spring. The groundwater field we can rather simply describe by classical hydrology, using Dupuy-Forchheimer's approximation for the water table, which is simply a mass balance of rainfall and flux, and the flux is driven by a static hydraulic gradient. This leads to a Poisson equation for the square of the water table above a certain datum. We can test this in our field site by solving this equation with the appropriate mean rainfall rate and a mean permeability, and then calculating what would be the flow inside the stream. And Alex Pedroff did this for these two channels in the Florida network and compared the predicted discharge from the model with measurements they did in the ravines. And even so that the model is a steady state averaged rainfall and rate, the instantaneously measured and the predicted look rather consistent on the one-to-one line here shown with a red line. Before we want to talk about the growth in the direction of the streamline, we simply look close to one of these channels heads at the bifurcated tip and ask the question, how does the flow field look? And what we see is that if the angle is wide, the flow line entering the spring here is curved inward. If the branching angle is very narrow, the flow line entering the spring is curved outward. So this means that if we grow in the direction where the flux comes, a wide angle would slowly become more narrow, while a narrow angle would open up in the time of growth. And we have a special angle in between where the flow line enters into the tip without curving, leading to a self-similar straight growth of the bifurcation. And the question which we will try to answer here in the next few slides is, what is this characteristic angle and how can we determine it? And to do this, we will use some tools that hydrologists had to use before they could develop big parflow and computational model, meaning complex analysis and conformal mappings. So here, for example, we have a straight river and a uniform flow field where the red lines are the flow lines and the blue lines are the iso potentials. And what you can do with this is that when you know the solution of one system, you can warp and bend it around to get the solution of another system. So here we bend this solution up to that the two ends meet, and we obtain the flow field around a single bifurcated, tip, which then will look like this. And we can ask what happens to the flow line entering into this tip. So this is the mapping from the upper half plane here around a single spring. For a bifurcated spring, this mapping looks a little bit more complicated, but can be expressed analytically, where these two lines running along the imaginary axis are mapped on these two flow lines that enter into the spring. So we said we look for the angle at which these lines enter the tip without curving. So we have to plug in the lines into the mapping, and we can express the curvature, which we can expand if you approach the spring, which gives this simple expression in a first order expansion. And what we see from this term is that the curvature vanishes when you go with the parameter to 0, if and only if this angle, this term disappears, which happens to be for an angle of 2 pi over 5, which is equally to 72 degrees. So having this mathematical result of growth in the streamline direction of a Poisson field, we go back to our channel network and look how we can measure the branching angles. This is how the valley head looks like when you are inside of one of these valley heads. And this is how a spring looks like. It's just coming out of under a tree or under a root and starting to form a channel. You see here that the leaves were washed away. This is when you reach a junction. And fortunately, we don't have to walk through all this network and measure the angles by hand, but we have a high resolution LiDAR map with approximately 1 meter vertical, horizontal resolution and 5 centimeters vertical resolution. We then used some topographic measures and flow accumulation to determine the channel networks. And we compared this also with several ground observation where we walked in the ravines and looked if we find the spring at the place where we had them on our tablet. Altogether, we have almost 5,000 junctions. We then measure the junction angles, and what we find is we will get a distribution which is rather wide, almost 25 degrees in standard deviation, but the significance of the mean is comes from the large amount of observation we have, and it's more or less 71 plus minus 1 degree. So almost close to, very close to the theoretical predicted angle of Laplacian growth. So what this result tells us is that in the case of these seepage networks, the shape and geometry of the stream network is determined by the surrounding groundwater field and not by the flow of the water within the stream itself. Additionally, we can summarize the first part that what we have shown that growth in streamline direction of a diffusive field favors this characteristic angle of 2 pi over 5. And second, that indeed, for the case of seepage channels growing in a groundwater field, this Laplacian growth process can be found, and that the direction of the diffusive growth has a branching angle of 2 pi over 5. I would like to note at this point that the theory is for a diffusive field, which is not limited to seepage. And we will see at the end that you can use these theoretical tools in a completely different way, which has nothing to do with groundwater at all. So going further along the channel, we can ask what are the drivers for the network shape in the plan form when we look from top, and what is the vertical. The plan form geometry is determined by the question, why do channels branch? And we can ask with respect to what we have previously seen, what is the angle at the confluence? Other factors are the topology, how channels are connected, so how many branches we have and how many side branches we have. And third, what are the scales? For example, the distance between the side branches here in this map. And because a lack of time, I will focus here on the branching angle for the geometry and the vertical profile for the vertical dimension. So if we start with the question, what are the controls of stream networks? I found this abstract by Alex Whittaker, who starts the abstract with a direct assessment that Earth's surface is shaped by tectonic and climate, period. And this was in 2000 something. And I suppose most people would agree with me that we agree with him, but it has shown to be rather difficult to quantify the amount of the different impacts of what tectonics is contributing and how much different climatic factors are controlling. And in the next few slides, we want to look how which parts are tectonically controlled and where we can find a climatic control. So if we go back to our basic course of hydrology and geomorphology, I took here a slide from the internet, which is from Alexa Calais, and which is said to be after Dunne and Leopold. We see that in arid regions, we have supposed to be high overland flow and high rainfall intensity, while humid regions may be dominated by groundwater flow, high soil permeability, and subsurface processes. So if we look at the stream networks in these two different places, we can see here that we have strongly incised by high flash flood events, while in places like here in Vermont, we have a much smoother, slowly varying landscape when the climate is humid and we have higher infiltration rates. So as we see when we compare already these two different channel network geometries, we see that there may be also a difference in the branching structure. And therefore, we may think that it would be interesting to see how the branching angles varies across the continental scale and how it depends on different drivers that change across the continental scale. And in this case, we use the North American continent because not only the NSA is good in collecting data, but also USGS is collecting data at the highest resolution and puts it in a consistent way for people to analyze. So the NHD Plus network, which was released in version 2 in 2012, has over 2 million stream segments. As you can see here, you only see a blue mass. It has millions of junctions, and it covers the whole continental US in a consistent way. We can then map the junctions, which is here. So you to see each junction is a single dot, and measure the branching angles of the two upstream parts on a confluence, where we used a linear regression model for fitting a straight line to a channel segment, a model which is invariant under rotation, because it should not matter if the stream goes this way or the other way around, or how we put our coordinate system. The climatic factors we can derive from precipitation and the temperature aridity, which the aridity index is defined by the ratio of precipitation divided by potential evapotranspiration. In principle, a proxy for how much the atmosphere is sucking out in water and how much rainfall it provides to the ground. And this is how the aridity index looks like. And in order to compare it with the branching angle, we will bin this into different basins. So it's a general procedure, which we will see a few times in the next slide, that in order to see patterns in this big data set, it's often a good idea to aggregate them over certain areas and then see how they compare. So we do the same thing with the branching angles. And if we put them next to each other, we see that there is a certain similarity. We see that the humid region in the east has rather wide branching angles like here. And we have notable wide angles in these humid regions along the Northern California coast and Washington, which also have wide branching angles. So in order to quantify this relation, we bin the branching angles with respect to aridity, the ratio of precipitation over potential evapotranspiration. So in each bin, we plot the mean branching angles, and we get this relation that we have low branching angles for in the arid places, and then increasing almost up to the 72 degrees in the most humid case. Also here, the result comes through statistical quantity, which means we need to aggregate several hundreds and several thousands of angles in each bin to get this consistent trend with small error bars. We then can look how the distribution of branching angles looks like in the humid place. And we see we have a nice distribution, which peaks close to the 2 pi over 5 case of the subsurface diffusive growth. And in the case of dry, arid landscapes, the branching angle is much narrower, meaning something like here 36 at the peak, or on average here, something around 45. So we can then ask the question, does this, how does this relate to what we know from geomorphology? And what we see here in the lecture slide is in arid region, we have high rainfall intensity, overland flow, and in humid regions, the subsurface flow is more dominant and the soil permeability. So we can try to test if we find some proxies that show this and how it relates to branching angles. So for the groundwater case, we use the water table ratio developed by Hachima and mapped for the US by Tom Gleason, and compare this with the branching angle. The water table ratio in principle quantifies how closely the groundwater field is connected to the surface. It includes the permeability or the conductivity of the soil, the recharge rate, and in some way, the topography. And it shows how the groundwater field follows the topography or is decoupled from the topography. So when plotting the water table ratio against the branching angles, we clearly see this trend that for very small water table ratio where the groundwater field is decoupled, the branching angles are narrow, which happens to be in arid climates, while for the highest water table ratio with closely coupled groundwater fields, we obtain wide branching angles, giving here a mechanistic relation between the coupling of surface processes and groundwater flow. On the other hand, in arid regions, we are supposed to be high rainfall, dominated by high rainfall intensity, extreme events, and overland flows, which can be characterized by the surface runoff erosion, surface runoff distributions that show or that quantify how rainfall is transferred into surface runoff. And already in 2006, Molnar and co-authors hypothesized that have shown that the frequency distribution of extreme rainfall events is heavier tailed in arid climates than in humid ones. It's still a question what the exact shape of this distribution is and how the tail has been described. But that the tail is more heavy is also then with much more data confirmed by a more recent publication by Rossi Whipple that measured the distribution of rainfall excess across the US in a more systematic way. We can then, what they have used as a parameterization for their probability distribution function is a stretched exponential, which has a shape factor CR, where small CR describe heavier tails, and when CR approaches 1, the distribution becomes exponential. So thanks to Matthew Rossi, who provided me the data, from his paper, and I just plotted his results with respect to aridity. And what we see is that when we compare this to the aridity angle relation, we see that the curves almost follow one-to-one each other. And this would mean that high runoff processes and how dominant the extreme events are shows mechanistically in the branching angle distribution. So more pronounced runoff in arid landscapes lead to narrow branching angles. So finally, we can summarize this, that the branching geometry is determined by the flash flood intensity, which is stronger in arid regions, and the coupling of the groundwater to the surface water in the case of humid cases, which leads to wider branching angles. The relation between branching angle and aridity is also not limited to the US. You can use a global data set and do the same analysis, and you will find similar corresponding patterns. And also the way that runoff excess and aridity are related is also to be hypothesized that it holds on the global scale, but with unfortunately more limited data that we can make the plots. So after having shown that climate determines somehow the plan form morphology of the stream network, we can look what happens to the vertical shape. And to do this, we will remember one of the most basic equations we know from geomorphology, which is that the change of the landscape is determined by the uplift minus the incision of the stream. And uplift is a mixture of tectonic and can be influenced by climate by removing the load, for example, due to melting of an ice sheet, while the incision term is then determined by rainfall runoff and how the flow incises into the surface. And recently, Chen and co-authors have published a paper on where they extracted the river profiles on the globe and introduced a measure how concave or convex a river profile is. Namely, they introduced the normalized concavity index, which is nothing else than the median of the deviation from the profile from a straight line. So concave profiles have a negative concavity index. A straight line would have a concavity index of 0, while a convex profile would have a positive concavity index. They map this on the globe, which you see here, as each single point on the map is a profile. And just to visualize you in a certain area, I plotted here the profiles, which are pieces of the whole channel network, not the whole channel network together. And they are approximately 30 kilometers long, more or less. And we have over 300,000 profiles, which we can then analyze. As we did before, to see some pattern in this data set, we did a binning with respect to river basins of the hydroshed data set. And what we already see is that some features jump out, like the Pacific Ring of Fire, which continues in the North American West Coast, the Nazca Plate and the Andes as highly concave places, the Alpine Himalayan mountain belt, which runs here from the Alps up to the Himalaya, we see Rift Valley, if we carefully look. And of course, we see the Himalaya, where the Indian continent starts to warp the Eurasian plate, and New Zealand. So in order to hypothesize how this mountain formation can be related to the concavity of the channel network, we look back at the basic equation. And what you would just think is that, well, mountains are built up because they're uplifted faster or stronger than their surrounding. Otherwise, they would not be higher. And usually the headwaters are in the mountains, which means something was lifting them up stronger than the whole rest of the landscape. So the hypothesis is what happens if we have a uplift gradient from the lowlands to the headwaters, and how does this affect the channel profile? And using a uplift gradient here with respect along the channel network, we can almost solve this model analytically and then calculate what is the profile concavity in the different cases. So here in the cases, if we have no uplift gradient, light blue. If we have a positive uplift gradient, which is higher in the headwaters than at the outlet, we have the dark blue. And if it's reversed, we have the orange curve. And we clearly see that if we have a uplift gradient with respect to the mountains, the concavity is much more concave, meaning a negative concavity index. So in order to compare this with a data set and with the data which we have, we need to find a way to quantify this tectonic motion, the warping of the surface. And it has shown that it is not so easy to get consistent global data smooth about uplift. So we used two recently compiled global data set, which is about tectonic activity or seismic hazard as a proxy for the amount of tectonic motion which is going on in these places. Namely, the two data sets are the global earthquake model by Pangini et al., just released recently, and the global seismic hazard assessment program by Giardini et al. From a few years ago. So this is back our map of the concavity index. And here we have our two proxies, which we see the mountain range along the North America and the South American coast. We see the Alpine and the Alpine Himalayan mountain belt, and also the Pacific Ring of Fire. Slightly, we see here Rift Valley. And also the two data sets are rather different in their numbers. They show a consistent pattern across the globe. And if we compare this with other controls that have been suggested, we find that these controls have a negative correlation here, while we have a positive correlation here in the Western US and South America. And again, a negative correlation along the Pacific Ring of Fire. So another control that is of course related to the mountain building is the topographic slope, which also sees that one would suggest that there is a rather strong positive correlation between concavity and slope. So to quantify our hypothesis, we bin the data with respect to the different variable. And I separated here the structural controls of the two tectonic data sets and the slope, and contrast them with respect to climatic data sets, where here we have the aridity index, precipitation, and potential evapotranspiration. And what we see from these plots is that the structural controls have almost 3 times higher explanatory power than the climatic factors. So climate seems not to be very important for the vertical shape. So summarizing this 2 factors is, we see that the planform geometry seems to be dominated by different processes that are related to flash floods and overland flow, and the presence of groundwater, which itself are related to climatic conditions. These lead to narrow branching angles in arid climates and wide branching angles in humid climates. While the vertical component is dominated by the competition of incision and uplift, and has a strong influence by differences in exhumation. So following the path of the channel network from the source to the sink, we finally arrive at the delta outlet. And deltas are more complicated than rivers because they're at this tiny balance between erosion and depositional environment, where small perturbations like storm surges, sea level rise, or a change in sediment supply could lead to a tremendous shift in how the morphology looks like. And what I simply want to show is a few slides where John Shaw's group applied the concepts we developed for the headward growth of the seepage channels to the delta outlet. And as I mentioned before, that the only thing we needed for this theory to apply is the growth in the direction of a diffusive field. So what he identified is that if you have a tidal channel network, the height of the water is described by a Poisson equation, as you can find in Ronaldo and al. And in this case, the ocean itself acts as a diffusive sink for the flow. So in this case, it says that the highest sediment transport would lead to less deposition and therefore create the branched channel network, which is in principle exactly a time reversed version of the original seepage problem. They then took a bunch of delta shapes and delta maps and measured the branching angles, even for an experiment. And what they found is that the experimental delta and the natural delta all have a peak around the 2 pi over 5 theoretical angle, which clearly shows that the theory is only related to the diffusive growth hypothesis and can be applied on problems beyond seepage itself. And in this way, we closed theoretically the loop from the source to the sink. And I'd like to thank you for your attention, for running with me through this channel network. Thanks.
Thank you, Hans. That's great. If you have any question now, if you want to ask directly, you can click the participants on your Zoom meeting. Then over there on the bottom right, there's a function called raise your hand. You can raise your hand, then you can unmute yourself, you can directly ask. And otherwise, before I give a little bit time to do that. So Hans, if you click the chat, here's the question from John B. Shang from University of Arkansas, you just mentioned. John
yes. Where is the chat?
So John asked a question through the YouTube. He's not in the Zoom meeting.
Okay.
So Yeah, if you read a question, he said, can you comment on why there are lineation through the network? Many channel axes line up with one another. If the bifurcations were selected from a probabilistic distribution, I don't think that this would occur. So can you comment on John's question?
I didn't really understand what is mean from the probabilistic. So I mean, you know, these channel networks have much more natural variability than just a theoretical growth. And, you know, you have a lot of perturbations that lead to different angles. Even, you know, the meandering and how the channels are curving lead not to a straight growth as, for example, a theoretical branching solution would have to. So it is, I suppose, quite natural to expect that you will find this results only in a statistical sense.
Over the YouTube, over there on the chat room, John said he means the Florida network specifically.
Which network?
Florida network.
And what does it?
You mentioned Florida, right? Florida.
Yes, yes. So he means why the Florida network distribution is so wide?
I guess this is what he means.
Well, I mean, you should just look at how complicated it looks like. There are leaves lying around. There is differences in permeability, which are not theoretical. So there are a lot of external factors that don't align with a theoretical description of purely Laplacian growth. And also, you know, the groundwater field is not exactly obeyed. So all these influences, which we did not capture, lead to perturbations away and lead to different branching angles. And the average way how this in the mean behaves, you can then only find by extracting through large data statistics.
Okay, very good. So Michael Stigler. Michael?
Yes, when you showed your map showing the branching out angle and the aridity, and there was in general a lot of agreement, but there were certain areas that stuck out as not quite matching. And I was wondering if that might relate to the climate at the time when those channels were established, and that there might be some historical information embedded into into where these differences occur.
Yeah, definitely. I mean, we didn't input the question of time and how climate changed. However, I think when we say the relative distribution of climate, you know, may not have changed so much across the scales of the formation of these channel networks, because, you know, that the west or southwest of the US was arid. It was also long before, even if the whole climate by itself was more humid or more arid. But definitely, you know, also with respect to variability, tectonic, then geologic factors in different places, where, for example, here the Platte River you see is a quite exceptional case from the structure that we shouldn't expect, you know, a one-to-one relation between two factors. And if you look at the correlation factors, they are not 0.9, they are 0.4, 0.3. So there is a lot of other stuff influencing how these things behave. And it's not everything is explained by aridity alone.
Right, it's still it's a very remarkable, you know, correlation.
And I mean, the nice thing is that we can try, you know, to interpret this correlation with respect, you know, to the different aspects how geomorphologists think that processes are related in these different environments, and that they're consistent with the way how we think that wide and narrow branching angles could be formed by the dominance of the different processes.
Okay, anybody else? Any questions?
May I ask a question?
Yeah, go ahead.
Okay, thank you, Paul and Hans. Thank you for excellent lecture. So my question is, I usually use the seismic profile to analysis how channel the distribution of the channel. So I found that sometimes the river is perpendicular to the fault, and sometimes the it is parallel to the fault. Could you tell me how do you understand this problem?
I mean, there is definitely structural control of tectonics, how river networks are aligned. And if you look here in the southwest, or here, that you have parallel foldings, that the main channel is running along the fault. And then you have the side branches coming in from the sides at almost 90 degrees. So this is definitely a topological factor, how the surface looks like, and in principle expresses how flows shape landscapes, but also how the landscape shapes the path of the flow.
Okay, okay, thank you very much.
Any other questions? Okay, so over on the YouTube channel, Jim Chapman make comments. Thank you for the presentation. So if you have any further question, you still can write an email directed to the Hans. And also, this presentation is recorded and available on the YouTube. So you can go back, rewatch this presentation. So on the chat, Uri also from Haifa also made a comments, a very interesting presentation. So I think I will see it again. Next, if no any question, next Wednesday we will have Irina. She will talk about the Greenland sediment with the global warming. We know more ice melt down, how much sediment really contribute from Greenland to the surrounding sea. I think will be also very interesting talk. Please do coming back. And once again, as I mentioned the last time, we want to have more people talk about other river system, particularly like the Russia 3 large river system, and also the Amur River, and also Shat Alaba River, and somebody maybe talk a little bit the Rhine and Ebro and the Congo, Niger, and even the Yukon River and the Mackenzie River. Those river in the high latitude area, and some South America river, San Francisco, and so if Orinoco, for example, if we are trying to be more inclusive, if you yourself or your colleague able to contribute a presentation, please let me know. Thank you very much. So
okay, then thanks a lot for having the opportunity to talk here, and I will join the next talks to listen to them.
Great. So if no any other question, we can stop here. Okay, great.
Thanks. Cheers.
Stay safe.